brand new function, alpha, equal the gradient of scalar, to play around with to make that equal to 0. Does it change any of the physics?
Nope.
Absolutely not. So can I do it?
Yes.
Okay.
As long as it's not changed other physics, they're all set.
That's right. Yeah. I mean, it does bug me at some point, right? You go, well, I kind of think that A's do matter, right? And potentials do matter. You know, doesn't it bug you a little bit?
Differences in potentials.
So that's what it is, yeah. So what we learn about potentials is it's differences that matter, you know?
Voltage we're measuring with respect to the Earth.
Yeah.
I mean, the Earth isn't really 0.
Right, exactly. And so in physics, what it really is potential differences of what we measure. All right, so we're okay. All right? So let's see what other conditions. All right, this is a little bit messier, but we got to work on the other one. Okay. So now we want the two potentials to give the same E. Okay, so we want, you ready? We want E to equal minus the gradient of B minus the partial of A with respect to T. And that has to equal minus the gradient of V plus beta, right? But then minus what?
D alpha plus A plus alpha.
Okay, and then partial of A plus alpha. Okay, so let's do it all out. So we end up with minus the gradient of B minus the gradient of B, beta, thank you.
Actually, beta, not B.
Yes, I agree, thank you. Minus the partial of A with respect to T.
Minus the partial of alpha with respect to T.
Minus the partial of alpha with respect to T.
Good.
Okay, so this thing cancels this thing. That thing cancels that thing.
So the derivative of alpha has to be 0.
So we need 0 equal minus the gradient of beta minus the partial with respect to T of alpha.
The time derivative of alpha is equal to the minus gradient of B.
Okay, well, I'm going to follow the book. I never would have thought of this, all right, but this is a clever step. The next step is on the next one on page 420, and it is the gradient of beta plus the partial of alpha. Oh, so wait a minute. Sorry.
Well,
No. Now I see what we're doing. Now we've got to plug in alpha. All right. So 0 equals minus the gradient of B minus partial with respect to T of what?
The gradient of scalar.
Gradient of lambda, and that scalar is lambda. The gradient of lambda.
Then you factor out the grad.
You can factor the grad out. So then over here you end up with a gradient
Of beta plus
of beta
partial of lambda over
lambda over T equals 0. Right? All right, and so what does that say? Okay, so this is a little bit subtle. What does it say about beta now, the partial of alpha with respect to T? Does it have any spatial?
No, it's time based.
Right, so it's essentially constant, right? It's essentially constant with respect to any type of space coordinates. So it's some constant space coordinates, but it could depend upon T, right? So the next step is that beta plus partial of lambda with respect to T. All right, that could have some type of time dependence, and let's call that K of T. So in other words, beta equals, and again, I'm just following the book here. This is too clever for me. All right. Beta equals minus partial of lambda with respect to T plus K of T. By the way, any old function, right? K of T. Okay. Okay, so then here's a very nice statement. Okay. So follow this in your book. Actually, we might as well absorb k of t into lambda, defining a new lambda by adding the integral of k t prime dt prime to the old one. All right, which is kind of subtle.
Right.
And I've had to think about that in a way to say that. But it just absorbs.
K of t into
Yeah. Yeah.
A plus the grade of lambda, and v prime is v plus minus the time derivative.
Yeah, so the final conclusion is that beta equals minus partial with respect to t of lambda. All right? So, you know, I haven't explained that one part in full detail. Okay? But I think we're okay. What the clear thing is that you have the partial of lambda with respect to t, and then some other function of t. So let me think, see if I can come up with an example. Okay, so what you're essentially doing is this. Is you're integrating with respect to time k of t. Now, if you differentiate that, what are you left with? So here's a good way to say it. Do you see
And
it?
then you're left with k of t.
Yeah. So watch. So let's let lambda go to lambda plus the integral from 0 to t of k of t prime dt prime. Okay, so this is essentially giving us the integral of k of t prime dt, right? But now, if we want, now what we care about is beta equals the derivative. So if we take the derivative with respect to t of lambda plus the integral from 0 to t of k of t prime dt prime, what does that equal? Well, it equals the derivative of the first thing, right? Plus the derivative of the integral with respect to time, which is just the thing itself. Okay? So what we'll do is we'll call this our new lambda. And that works out fine, so I'm glad I did that. Like, I think that example is better than saying it in words. Right?
Minus lambda plus.
Okay, yeah, we've got minus lambda over there. So we've got beta equals minus lambda.
No,
Okay.
minus derivative.
Okay. So, so look, what we've got over here is the following. We've used this gauge trick, and everything will work out just fine. Our flexibility is built into the idea that we could have that A prime now has to go to A plus, what do we have? The gradient of lambda. And V prime
Has to go to v plus.
goes to V
Minus the time derivative
plus minus the partial of lambda with respect to t. Okay, so what does this mean? So look at that and tell me what it means in words. What is lambda?
any function.
Any function. Right? So
You can add any function to the vector or scalar potential, and it's not going to change.
okay, let's say it a different way. I can take any scalar function lambda that I want, right? And the gradient of it will be such that its curl is 0. So we'll give you the same vector potential A.
Yep. And the scalar,
But at the same
we
time,
added,
And using that same scalar function,
take time
Time
derivative of that
derivative
plus the original
minus.
vector, the original scalar potential will give you a new scalar.
and that, but
The curl of the new scalar potential is going to be the same as
not the
the
curl
gradient.
of it.
The gradient of the scalar
The
potential.
gradient of it minus the partial with respect to E, to A of this thing. Okay? So that's the new deal. I can pick any scalar function, and then that's my new A prime, and then this thing makes my B prime. All right? And that preserves my
Maxwell.
doesn't change the math.
it doesn't change, it might make the math easier, all right, it will make the math easier, but it preserves my electric and magnetic fields that I want. It might pervert them too, I mean, it's kind of screwed right now, right?
It's pretty perverse.
Yeah, I agree. Anybody else who would walk into this class would think that this was kind of crazy, all right? And perverse, I would say.
Yes.
All right, so that's the idea. Okay, so now what we're going to do is we're going to use that flexibility all right, to be able to add this thing to make this thing 0. All right, and that will be called the Coulomb gauge. And then we'll find this thing to make this 0. Well, you'll find, so in other words, we'll find the scalar function lambda that makes this equal to 0.
And then make that equal to, so make the curl, the divergence of A equal minus.
Okay, here's the screwy thing, is that you never really have to do it. You actually never have to find it. All right? All you really have to do is say, like, we're not interested. Like, ultimately, were you interested in this thing? No. I mean, so ultimately, our goal, so look. Maybe I can write this a new way. I think this is going to be helpful. So now let me rewrite this as, now I'm going to be solving del squared B prime plus partial with respect to T, and the divergence of A prime equals minus rho for epsilon naught, and then del squared A prime minus mu naught epsilon naught partial squared A prime with respect to T prime minus the gradient of the divergence of A prime plus mu naught epsilon naught partial B prime with respect to T equals minus mu naught J. Okay? So watch this. Let's work first in the Coulomb gauge. All right? And the Coulomb gauge is to say, let's find this to be 0. Now you can find the conditions for it to be 0. But what are we really interested in solving for? E and B, right? And how can you get E and B? From A and A prime and B prime, right? So if this equals 0 and I solve for B prime,
That's B prime.
that's B prime. Did I ever care about what this was?
No.
Okay, that's the most crazy argument I've ever made. All right? And Eric, I think you got it.
Well, we know it's mathematically true because we've proved that before.
Right.
As long as we can get
So
A and B.
that's still the same thing.
And so it's the same
Just
thing.
looks weird.
So does it even matter anymore that I ever worry about this?
No.
Don't need to really call them primes.
Or do I ever have to even call them primes?
No.
It only matters what gauge you are.
Exactly. Exactly. Just say, all you do from now on is say, I'm in a Coulomb gauge, okay, that's 0, solve it. Right? Or I'm in a Lorentz gauge, that's 0, solve it. Because the V you're solving for and the A you're solving for is going to work.
Well, I don't want to forget all the fun I had.
All right, so that's it. That's gauge transformation and that's gauge freedom. And so I kept putting primes in my notes and everything.
It doesn't matter.
But it doesn't matter.
Because no matter what you convert A, it's gonna work.
Right, what, yeah.
No matter what we're looking for.
Well, it's more, don't worry about picking anything. Here's what it is. Don't worry about picking anything. If you solve this, it's going to work. It's true. Right?
Yep.
Okay. Isn't that neat? That makes your head scratch. That's one, okay, so at least I have someone scratching your head. All right? So that's kind of like one of the head scratchers that I always think you get when you do separation of variables. And you know you get it into a function of x plus a function of y equals 0.
Yeah.
And that means that this equals a constant and this equals
Separation of
no, that's kind of what I call a head scratching moment. I don't think it's intuitively obvious right away that the function of x and the function of y are each equal to a constant. All right? I mean, I think you guys feel like it and it's obvious now, but when you first presented with that, you know, that's kind of a head scratcher.
Didn't we have to prove that in quantum mechanics?
What we did is, yeah, I try to give you a couple functions to show you. The question is how can you have a function equal to a constant? All right? Like, how can you get a function? And I gave you an answer. It was like an e to the x. It was like a derivative of e to the something divided by the something.
We had to use e to the something.
Yeah,
It's the only function.
and it worked.
Yeah.
Okay? But anyway, this is one of these counterintuitive arguments, and we just went by the hard part of the argument. All right? And now we'll just solve it. So we're done. All right? So forget about that.
No, don't forget it.
Well, yeah, well, you guys can't forget it. But, you know, one of you guys said it. You know, you just said, I'm going to be in the Coulomb gauge. I think you said it, right?
Yeah.
And then you just say I'm going to be in the Coulomb gauge, and that's it.
You just say which gauge you're in.
That's it. Yeah. All right. Now, what's going to happen is in one gauge, you're going to get, you know, like the Poisson's equation. It'll be very easy to solve for V. But then check it out.
Yes.
That change makes this messy. All right. And so if all you're interested in is like the potential, well, no, you still need this. So you still need A. So the Coulomb gauge is of limited use. But
Because you still need A to find what the E is.
right, you need
You need A to find
you
both
need
E
A
and
to
B.
find just B, and you need
A
and B to find E.
So you can find V really easily.
But you can't find A.
A is not so simple.
Yes.
He's the annoying guy.
What's that?
He's the annoying guy.
Yeah,
You need
because,
both.
well,
No, B-
yeah,
they both are.
because even in the Coulomb gauge, you don't get A easily, so A is annoying.
Yeah.
Okay, so that's exactly what we're going to do. And so let's kind of look at that, and that's kind of in section 10.1.3. Right? Okay, so in 10.1.3, we were going to choose to live in so decide to work in the Coulomb gauge. Okay, that means I have decided to make, if you'd like, this is how I wrote in my notes. I had decided to make that 0. You know, put the prime in there just to emphasize. Okay, I decided to make that. All right, in which case you could solve it and put it in. you put it in this thing, in the divergence of A, you could find a real scalar function that made that work. Okay, but we don't care.
Right.
Okay? So in that case, what you're left with is divergence, the Laplacian of the scalar potential. And if you want, you can put in the primes, but I'm going to not put in the primes anymore because it doesn't matter. All right? That equals minus rho free over epsilon naught. This is the Poisson equation. Okay? And I'm not going to go back and do this, but you did this in EM1. You were able to solve for this. All right? And I'll tell you the page it's on because I went back to look to see what page it's on. And it's on page,
So there's
geez,
no
I thought I
exceeds.
looked at it. Oh, page 84. So if you look way back on page 84, you will have the Poisson's equation.
Oh, yeah.
Yeah, it's there. And how to solve it. And the way you solve it is as follows. So let's get everything right. The way to solve it, so the solution to the Poisson's equation is V of R and T is equal to 1 over 4 pi epsilon naught, the integral of the rho free of R prime T over little script r d whatever the hell that is. So tell me what the hell everything is there.
Well, the squiggly r is the separation vector,
Yeah.
and you're summing up over all the integral.
What's the integral over? What's that
tau.
symbol?
That's volume.
Volume.
That's the
So
volume.
that's what Griffiths uses for volume.
That's
Okay.
the integral of.
What's that?
It's in the cover.
Yeah, he uses that. So look, if we had to do a picture of this, so this is where I think a picture is really important, all right, or a sketch. Okay. Okay, so let's see if I can do it. Let's say that I had a blob right here. Right. And this is a blob of charge. Yeah? All right. So this is rho. Right? And I wanted to find out the potential right here. So I want V of R and T. So I'm labeling this as R. Right? So what would I do for go about labeling where I am in the blob?
Make that the squiggly r. You have another vector, then you have a separation vector between those two.
Okay, so I agree with the separation, but what do I want to call where I am in R? Not the separation yet. Where I am in the blob.
Maybe R prime.
That's R prime.
That's our prime. Yeah.
Okay. So this is R prime.
Yep.
Okay. Yeah, it's really good to draw this out and make sure you know this, right? It's,
Yeah.
yeah. Because what happens is you get kind of complacent, you look at it, and then you go, oh, it's obvious, and it's not obvious.
It's not,
Yeah. Okay, so then look, I have vector R right here. So this is going to be rho of R prime, all right, and T. Okay, but then what do I need to know? I need to know the distance between them. So look, here's how you add vectors. Here's R, here's R prime. So if I went tip to tail, here's R, and then I added R prime, it would be out there, right? And then the final vector would be out there. So that's wrong. Right? So what I want to do is go R, and then go minus R prime. So instead of going out that way,
Coming down.
do it. And by the way, if you guys tutor, I need you guys to really nail the vector addition, because my 181 kids can't do it. Right? They get it wrong every single time. So in some sense, like I think a lot of even physics majors, you're too lucky or too smart most of the time. Because most of the time you guys know the answer, right? But when it gets a little bit tricky, sometimes when you're too smart and you know the answer already, then you don't have anything to fall back on the harder problems. So it's always good to go way back to the basics of how do you add vectors tip to tail. Okay, so here's R, all right? And then this is minus R prime. And then the resultant vector goes from where? goes from the tail of the first
To the tip of the
to
second.
the tip of the second. So this is R. All right, and that equals R minus R prime. Now, doesn't it bug you that it's over there?
No, it's translational.
You can just translate it, right?
We're in flat space, so
Well, yeah, so in other words, that's R right
we're in
there.
Minkowski space, so we can do
Yeah, I mean, look, here's how I'll explain to students. If this is a vector length 1 and it's north, right? What is it now? A vector length 1?
No.
North. What is it now?
Vector length 1 north.
Yeah.
In
Okay.
flat space.
Ah, Jeremy, you like that one. You've never seen that one. You're
No, I
smiling.
like it. I've
Okay.
seen it before.
Oh, okay. Oh, you're just laughing at me doing that. Yeah.
Living in flat land.
All right. Well, at least I think this is a decent one to have on lecture. It's not one like
Oh,
that
yeah.
ones. All right.
This is gonna be good.
Okay, so that's it. And then what is dV? I mean, this thing.
The tau.
Yeah. So, you know,
That would be, we're summing over the whole volume of that blob.
yeah. So we're going over whatever that blob is. If it were in Cartesian coordinates, it'd be dx prime, dy prime, dz prime.
Yeah.
If it were in spherical coordinates, it would be,
dr prime, d theta prime, d tau, d phi prime.
okay, it would be,
R
careful,
theta.
r prime squared,
Yeah.
Yes.
Then
dr prime, sine
Sin
theta, sine phi.
Yes.
D theta d.
Yes.
Yeah, I think I got it.
Sin theta d theta d.
Okay, yeah. All right, so there we go. I want you to read the paragraph that Griffiths talks about in the middle. It's very subtle, all right, having to do about time and everything like that. It's subtle. I can't do it better than he does, and I want you to read it. I want you to think about it, all right? So that's the advantage of the Coulomb gauge, is that it's very easy to calculate that potential. All right, the disadvantage is,
You
all right,
still need A.
yeah, so look at, so what you end up with is if you plug this into, so you plug, so the disadvantage is, so this is easy. So this is from 10.4, all right? And now we have 10.5. And again, what are 10.4 and 10.5? They're just,
gauge.
Representations of Maxwell's.
those are just
Yeah, they're
Maxwell's equations, yeah. So now you go to 10.5, and you let the divergence of A equal 0, and yeah, you wipe out this.
Then you still got.
But you still have all that other stuff. And it's quite nasty to look at. It's 10.5 reduces to the Laplacian of A minus mu naught epsilon naught partial squared of A with respect to t squared equals minus mu naught j plus mu naught epsilon naught, the gradient of the partial of V with respect to t. Okay? So that's messy as hell. Okay? So that's tough. So what we'll do is, I mean, this is tough. I mean, you have this in here, you can put that in there. But now to solve for A is tough,
Did you
right?
say it
Because
looked
you
like
have this other term here.
You say it looked like a wave equation?
Well, it does. It still looks like an inhomogeneous wave equation, but it's a worse inhomogeneous wave equation because you have that.
Yeah, that's
And so you have to solve for V, then you have to take the time derivative of V, take
And
the
then-
gradient of that
Yes.
in order to solve A.
For A, okay? So that's the Coulomb gauge, all right? So let me erase this,
Lorentz
Right.
gauge.
and then we'll go right to the Lorentz gauge. And that's where we're gonna do the rest of the stuff based on, okay? So in the Lorentz gauge, so let's try the Lorentz gauge. And there's good reasons, by the way, although I can't come up with them on the top of my head, but there are good reasons to work in the Coulomb gauge, all right? In quantum 2 and in particles, we do work there, but I can't do it off the top of my head, all right? So in the Lorentz gauge, and in the Lorentz gauge, what we're going to do is we're going to say the divergence, we're going to choose a lambda